Hello, in this video, you will learn how to fit a multiple linear regression model in R. First, let's read in the dataset. As you can see, the variable sex and CHD fate, they look like categorical variables. Okay, so let's do a contingency table on these two variables. And that confirms that they are categorical variables. And because they need special treatment in the multiple linear regression model, so that's why we need to check if they're actually categorical variables. Next, let's just take a look at the dependent variable. So the research question is, does BMI impact the systolic blood pressure? And not only we just want to look at the simple linear relationship between SBP and BMI, there's some other concerns. One is how to control for the impact of other variables such as age, SEL, follow-up, etc. And are there confounding factors such as age, right? Are there interactions between BMI and the sex, etc., etc. So first, we want to find a multiple linear regression model to model the joint effects of all these variables, and then we want to check if there's a confounding effect of age, and then we want to see if there's any interactions between sex and other variables. Okay, always do some plots first. This is the histogram of SBP. It's a little bit skewed, so we do a little bit transformation, the log transformation. You can see in this line of our codes, we use factor, factor sex and factor CHD fate. And when we use factor, R will do the dummy coding automatically. So we can do model and then summary. And you can see here, this is the outputs. So you need to learn how to interpret these outputs from the LM function in R. First, the F statistic is for the overall null hypothesis that fitting a linear regression model is significantly better than the null model, which is the model with the intercept only. And here, p-value is very, very small. So yeah, it's worthwhile to fit this linear regression model. And then the residual standard error printed out at 0.139. This is actually the square root of the MSE, the mean square error, which is a kind of a metric for prediction accuracy. Also, in this output, we can see information about how many observations were deleted due to missingness. So in here, we are not going to treat the missing data, but in this output, R will tell you if any observation was deleted due to missing data. Okay. And then the other two important statistics in the output are the multiple R squared. As we know, this can be interpreted as the variance in Y that can be explained by its regression on all these independent variables. So, and this is a measure of goodness of fit. Okay, so here it's about 0.25, so it's about 25% of the variance in log SBP can be explained by its regression on all these variables. And the adjusted R square is the R square and adjusted by the number of parameters. So it's kind of a compromise between the goodness fit and the model complexity. Here, the adjusted R square is 0.2565. So even though we have, I don't know, about 6 independent variables in the regression model, that really does not make the R squared deteriorate much. Okay, so then the coefficient table is where you want to look for statistical significance of the independent variables. You also get the parameter estimate, the betas and the p-values from like a Wald test. And these outputs are marked by the star system. There's a significant codes. With 3 star, it's almost 0. 2 star is less than 0.001, and et cetera, et cetera. Okay. So basically, like you can interpret this model saying something like, the linear regression model of log SBP on log BMI, age, sex, months, follow-up, CHD fate, and log CL, SSCL is overall significant, and you can cite the F statistic and the p-value, and then with an R square of 0.2576 and R square adjusted R square of 0.2565. And based on this model, the log SBP with beta equal to 0.268 and p less than 0.001 is significantly associated with log BMI after controlling for age, sex, months, follow-up, CHD fate, and SCI. More detailed explanation is with 1 unit increase in log BMI, there is 0.268 increase in log SBP. Okay, so this is a kind of a sample interpretation to interpret this multiple linear regression output. And there's some additional output you can get. Just want to show you. So for example, the names of the model 1 that we have fitted, it give you, these are the kind of attributes of the list of the model 1. And you can look at the structure, give you more details about each component there. And then you can do predictions. You can predict the values using our command predict. And then, of course, you can use a plot to plot the residual plots. And also you can use the CONFINT, confidence interval function, to calculate confidence intervals for beta. Okay, sometimes people prefer to use confidence intervals to present regression outputs. If you are making, for example, making a table for your regression results, it may be a good idea to put confidence intervals there. So you can use this CONFINT function to calculate the 95% confidence interval. And then, of course, you can always generate this ANOVA table, which should give you sum of squares and p-values for each of the overall significance of the predictor, independent variables. Okay. And also the ANOVA function can be used for comparing two models. For example, if we fit another model, model 2, in which we do not include age. Okay, so fit this model without age. And then the model 2 is nested within model 1. So we can use ANOVA to compare the two models and to answer the question if model 2 actually is significantly better than model 1. Okay, so here p-value is really small, and this says, yeah, age does improve the model fit significantly. So we'd better keep it there. And to check for confounding, we are going to use a rule of thumb that is the unadjusted minus adjusted absolute value divided by the absolute value of unadjusted. Then we'll if this ratio is greater than 15%, we think that variable is a potential confounder. So let's do that to look at the age. Okay, so here let's just print out the outputs again and grab the beta for the for age. So one is 0.268, the other one 0.299, and then we calculate this ratio, and here it's 0.10. So the confounding effect of age is not too obvious here. So based on this rule of thumb, of course, this is not a proof or anything. So this rule is like really a rule of thumb. Okay. Then again, if you are interested in learning about interactions, sometimes they call moderation, and you can easily do this in R by using the interaction term, which is one variable times the other one in the model statement. Okay, so here you can see there are one significant interaction is sex by age. Okay, so this is there's no moderation for sex on the BMI effect on SBP, and there's no interaction between sex and SCL. Okay, that's all for this example. This example contains the basic kind of analysis for a multiple linear regression analysis.